Well, welcome, geology class. Here we are, online lectures. I like my red-green shirt. As the email that you should have gotten last night talked about, I'm coming to you because, well, I'll explain that in a second. First of all, a couple of you lodged a complaint against me with administration, stating that you felt I had exposed you to coronavirus last Tuesday, and that's why that email came out. Wanted to make it clear what's going on. When I was in class last Tuesday, I had not been in contact, to my knowledge, with anybody that had at that point tested positive for the virus. Furthermore, I'm pretty sure I was not within 6 feet of him for the required 15 minutes, which would preclude or prevent me from being on campus. So there's really not a risk of exposure at that point last Tuesday for you folks. Furthermore, the clothes that I wore were 150 miles away. I had 2 showers, so I'm not going to be carrying viruses into class. Suspecting a number of you have fallen prey to some of the hype and misinformation surrounding coronavirus. The deal is this: if you're going to become contagious, you have to basically get the virus into your body, and the way that happens predominantly is you get it into your lungs. It has shown an affinity for the ACE2 receptor in your lungs. ACE is angiotensin converting enzyme that is in the pathway that regulates your blood pressure. Interestingly enough, this virus enters your body because it attaches to the receptor for that enzyme and gets into your lungs. And so once it's in your body, there is an incubation time before you begin shedding viruses. Typically, you begin shedding viruses from anywhere from 3 to 5 days is that optimal period. And I was in class about a day and a half after I'd been hunting with my friend. So you were not at any risk. Any risk that I carried into class more than anybody else you rub elbows with in the hallway. Let's see, what else did I want to say? Okay, so the reason then that I'm not in front of you today is because in a separate matter, I did get exposed. My brother tested positive last week for coronavirus, and so I am in quarantine. I think it's till December 7th is what I'm told. And so we're going to have 2 lectures online this week, and I'm going to try to do something with the lab. I'm not quite sure how I'm going to do that yet. You have to have participated in 10 labs to get the D component, D credit for this course. And I need to add that up and make sure that you've done that. So we'll see if that's, well, we're going to have a chance for one more lab next week anyway. So that should hopefully put you all over the top for that required 10 labs. Okay, so for today, then I wanted to just pick up with a couple of items that I alluded to last time having to do with streams. And one of those items revolves around, well, I told you about how the Army Corps of Engineers is working diligently to keep the Mississippi in its course right here, current course, because there are well-maintained shipping channels that are conduit for the interior of our country. The Mississippi River, however, wants to go down this course right here, which is the Atchafalaya. And if we zoom in on this particular spot near Simmsport, Louisiana, actually just upstream a bit from that, right here, this is where the Mississippi and the Atchafalaya part ways, if you will. So this whole area is the delta region, if you will, for the Mississippi River. The Mississippi River comes down here, and this whole region here is delta for that tremendously large river. And so its course is going to switch throughout this whole delta region from time to time through history, and I've shown you the image of that, where the delta has been in the past for the Mississippi. So if we zoom in then to this particular spot, we can see some of the structures that the Army Corps has engineered here to keep the Mississippi where it's at. and they're right here. Now, if you can see, well, I don't know, I don't think you're going to be able to see with screencast on this portion of Google Earth. You can go there for yourself if you want, but I'll put the hand here, and down in the lower right hand corner, if you remember, a number of times in this class I've had you look at the elevation. Right here, the Mississippi is at 44 feet in elevation. That's 44 feet above sea level right here. If we go over this structure right here to the Atchafalaya on the other side, it's at 32 feet. This is 12 feet lower than this is. So you can see, were it not for this structure right here, the Mississippi River would definitely be flowing down the Atchafalaya Channel and not down the Mississippi. And this is another here. So if we zoom in on these a little bit more, you can actually, it's not the best imagery, but you can see what's going on here. And in fact, we can kind of go right down to that spot, and we'll go, oh, let's go right here, and we'll take a little hike across that bridge. Again, this is from like 2008. Let's see, I'll move it a little bit so you don't have to look at my mug. Okay, and we'll just zoom it. Maybe we'll zoom across. I think I can do that faster. Yeah. Okay, and I'll spin it around a little bit here. Okay, so there's the Atchafalaya, and the Mississippi goes by out here 12 feet above. So this water on this side is 12 feet higher in elevation, oops, than the water on this side. So that's what some of your tax dollars are going to maintain. This system that keeps the Mississippi in its current channel and doesn't allow it to go down the Atchafalaya, which is where it would tend to go, were it not for these two structures that have been built here and here to keep it in this channel. All right, so I alluded last time also to when we were talking about what was it? Oh, channel shape. That was a channel shape. And so if we look here, here's a wire that I've got. See if I can get it in focus. A wire. This is a V-shaped channel, and this is meant to represent a U-shaped channel. Okay, so here they are together. And what I want to do is prove to you that if all else is equal, cross-sectional area, so if these represented the same cross-sectional area of a stream, that there would be more perimeter in contact with the stream with the channel sides with this V shape than there would be with this U shape. Okay, here we go. So for the V shape, first I'll measure it here, and you know, you're not going to be able to see this real good, but you could kind of figure out what I'm doing here. I'm just measuring this V that I've made here, and it's right about, let's see, you can see right there, 25.5 centimeters across here, and it's 18 centimeters tall. So, no, turn it this way. 18 centimeters tall, 25.5 centimeters across. Now, if you remember, the formula for determining the area of a triangle is 1/2 base times height. Okay, so if the base is 25.5, and we multiply that times the height, which is 18, we get that. And if we take half of that times 0.5, you can see we're going to get roughly 230 square centimeters. Okay, so now if we do the same for this U-shaped channel, okay, let's clear that. So this U-shaped channel, okay, it's about 24.2 centimeters across there, and about 12.1 centimeters up here, up and down. Okay, so 12.1 would be, let's see, if it's 24.2 across, the radius of this would be 12.1. The halfway across would be 12.1. The reason I'm saying that is because if we want to figure out the area of a U shape, notice the U is actually half of a circle, and you know the area of a circle is pi r squared. Pi times the radius squared. Okay, so the radius is 12.1, and so if we go 12.1 and then times 12.1, I'm doing it really longhand here. We get that, okay? And pi, so times 3.14159, we'll stop with that many digits, equals that. But now we've got a half of a circle, so we're going to take half of that, so we'll multiply it times 0.5, and once again we've got just about 230 square centimeters. Okay, so mathematically then I have shown that the areas of these two features, this V-shaped channel and this U-shaped channel, are about the same. Okay, so these would represent stream channels. So if I take them now and I straighten them out, okay, I'll do my best to straighten them as straight as I can make them. There. Okay, so what I want to do is I'm going to hold these side by side so that you can compare these streams. So what I've in essence done is I've taken the stream channel and I've straightened it out into a straight line. Now if we stand these up, I'll hold the bases the same. Okay, this is the V shape right here, and this is the U shape right here. So I've got the bases the same, okay? See, they're the same. If you look up at the top, this is the V shape. It is, let's see if I can hold that against my black shirt so it shows up a little bit better. You can see that the V shape is clearly longer than the U shape, illustrating the point that if you have a V-shaped channel, you're going to have more perimeter in contact with the water, and that's going to create more friction. It's going to slow it down. If you've got a U-shaped channel, you have less perimeter, shorter wire, less perimeter in contact with the water, less friction, faster flow rate. Okay, so just a little visual representation of what I was talking about last time. Lastly, I want to go to, for this throwback to last class, I want to go to here. I want to go to Bethel University. I'm not actually there. I'm in my daughter's bedroom, but hence the froofy curtains and all the stuff behind me. This is my daughter that got married, so I'm able to abscond with her room. So if we look at Bethel University here, the Bethel stream, which is actually drainage ditch number 42 or something like that. Okay, it starts right here. It snakes its way along the back entrance, and goes underneath the road here and travels along here. I wish I was in class to ask if any of you have ever taken the float trip ride down Bethel Stream after a good rain. I know it was a big deal for a while. They used to have a grate right here. I'll zoom in on this a bit, to keep people from going down the culvert. Okay, because that culvert then goes underground here, past the CLC, underground here, comes out on the road here, and woof, out into Lake Valentine it goes. So people used to hop in there with flotation devices and you know, take a screaming ride down the stream. So they put a grate there. Genius idea, because the grate is going to catch all the debris from upstream and make a dam. So that came out. I got to look there. I'm not sure what's there right now. But at any rate, that is not where Bethel Stream used to go. So this would be the course currently of Bethel Stream, okay, right there. It used to flow around here, make a pretty sharp bend right here, come back around here, and flow out there. All above ground, none of it in a culvert. Culvert is the tube that you would put under a road to carry a stream under a road, and on top of which you could build a road. Okay, so there's a culvert here. This is all culvert. And some of you have been to Bethel long enough to remember, was it 2 years ago that caved in right there and they had to replace the whole thing? Okay, so my question to you then is, knowing all the factors that go into stream flow, what effect did straightening Bethel Stream and putting it in a culvert, a concrete tube this whole length, what effect did that have on its flow rate versus when it flowed above ground, not in a culvert, with sticks and rocks and gravel and all kind of debris in it that the water had to flow over and around, and it flowed right past this corner here. One of the reasons they moved it is because it was eroding this bend pretty actively, and they had, were worried about it eating into the bank and doing away with the road there. So if you think about it then, if they straightened it, put it in a tube, if you think about those variables of stream flow that we've been talking about, what effect would that have on the stream flow of Bethel Stream, doing what has been done to it? Okay, let's see, what else did I want to say? I think we left off with ultimate base level being sea level, with notable exceptions, Death Valley and the Dead Sea. I think I stopped with graded stream. I'm not sure, I'll just mention that again briefly. A graded stream is a stream in which all variables of stream flow are at equilibrium in the main channel. And by that I mean there's just enough water, just enough velocity to carry the water and sediment that it has gotten at that point. And none of it is deposited that's being carried past that point in the main channel. So the water and sediment that are going past that point is going just fast enough that it carries the sediment that it has, but it doesn't pick up any more off the bottom, nor does it deposit any more on the bottom. It's at equilibrium, just the right amount of speed. So, and that's true for all those variables. They're all the shape of the channel, the gradient, all that stuff works together so that there's this perfect balance where there's just enough of all those variables are set just right that there's no erosion or deposition in the main channel. We would call that a graded stream. Now, in reality, a graded stream doesn't actually exist. But it is what all streams are striving to. I shouldn't say that. We know of no graded streams. There may be some areas of some streams that meet that criteria. Don't know of them. But that is what all streams are tending towards. I already talked earlier at this section about how streams in Minnesota are fairly young because glaciation destroyed many of them, and how streams, we compared it with Kansas, the streams are much older because they were not glaciated. And so this idea that streams will age and take on different characteristics is one that we can see in our country with the newer streams we have in Minnesota, older streams we have south and west of here. Let's see, what did I want to say? Okay, we'll go to a picture here. If you think about how streams erode a valley, an area through which they are flowing, there's a good example here. This is the Yangtze River in China that we talked about last week. And the Yangtze, as it's flowing, honestly, I don't know if it's flowing, which direction it's flowing in this picture. I think it's flowing into the picture, but I'm not sure of that. So while it's flowing, it's actually affecting this stream valley through which it is flowing. Water is flowing down here, and the stream is rubbing against the sides of the valley. It's steepening them, and then they topple in when they steepen. So this stream is actually widening the valley through which it flows over time. And so it's also deepening as it's moving bedload along the bottom. It's bouncing and skidding and rolling stuff along the bottom. It's eroding the bottom of the stream channel and scouring it out and carrying that sediment away to the China Sea in this case, and changing the bed over which it flows, deepening it. So it's widening it, it's deepening it, and it's also lengthening it. If you look at your notes, we talk about slope retreat. That is as these slopes are getting wider through time. We talk about down cutting, and that's as the channel deepens. And we talk about headward erosion. And so if we go back to Death Valley, oops. Back up here, okay. And we look at some of those stream systems, they're so well delineated in this part of Southern California. That's why I like to use this as an example. So I'm just going to randomly pick one here that seems like it might have a good image that we can use. Yeah, that's a pretty good. We'll go with this one here. So here we have a nice, well delineated stream system that comes down here. So through time, this stream is going to eat away at the divide right here between it and the neighboring system on this side of the divide. So here would be the divide, and through time, these streams are going to compete. Now, this one being larger may be eroding headward. Okay, so headward erosion means lengthening the stream channel by eating into the divide. It may be eroding headward more rapidly than the one on this side. It's a bigger stream. That's a reasonable assumption, but it's not necessarily so. There can be some smaller drainage basins that are on very erodible sediment or have a lot of water in them or have a steep gradient, and they'll be eroding more rapidly. But let's just say that this one is eroding more rapidly. So headward erosion is going to lengthen the stream channel as this divide is eaten into by this tributary and lengthens that river system. Now, if you think about it, that's what also goes into making waterfalls migrate upstream. And when we were at Taylor's Falls, at Curtain Falls specifically, I was talking about that. So the stream, when it is flowing here and flowing over this lip of Curtain Falls here, it falls down and it splashes. It eats away underneath this waterfall until this can no longer take that much strain and it caves in. And then the waterfall moves upstream a little bit, it continues to cave this back, and then this falls over, and that waterfall will continue to migrate upstream through time because of headward erosion and because of the potential kinetic energy of the water going over that rock edge. Okay, so again, streams erode the valley, the channel through which they flow in three ways. They make it wider, they make it deeper, and they make it longer. And as they're making it longer, waterfalls might migrate upstream. And there's one other thing that can happen as a stream makes its channel longer. So here's the divide. If I look down there, this is at 10,376 feet. So if we go down here, we're going down to 9, 8, 7. Okay, so here's the divide, and we go on this side, we're going down to 9, 8, 7. Okay, so here, this is definitely a divide right here that separates this stream system from this side. Okay, and so if this larger river system were to carry, let's see if I can zoom in on that just a touch more. Okay, so if this larger stream system were to eat at this divide, and these little tributaries to this smaller stream system could actually be stolen by this stream right here. Now I'm going to go to one of my favorite sites, go to Wikipedia. This is actually a topic called stream capture. Stream piracy is what I have in my notes. And here we have a previously existing stream. This is upstream, this is downstream, so it's flowing in this direction. Okay. Next door, we have another stream, and this is its headwaters, and it's eating into the divide here, eating in, and then eventually it will eat through, and it will actually divert some of this stream's flow down a new course. Excuse me, down its course. And so this would be called stream piracy here then, as this stream right here used to flow here, and this stream here, but now all this water goes down this stream, and this stream channel right here is abandoned. An example of this is right here. This is the Maumee River well, you can see right here, you got Ohio, Indiana, Michigan involved in that Lake Erie region. And it is flowing this direction. It has lengthened its channel. The St. Joseph River and the St. Mary's River, they're actually flowing kind of, well, one northwest, one southwest. And they used to flow into the Wabash River, as mentioned at the bottom of the screen here. But because the Maumee River had eaten its way into the divide, the flow rate of these rivers has been diverted, and they no longer flow west down the Wabash River. Now they flow northeast down the Maumee River into Lake Erie, and the flow rate of the Maumee then has increased because it has now increased its drainage area. Okay, so a real-life example of stream piracy, not just something in the mind of geologists. Okay, folks, I think that's where I'm going to leave streams. And I don't want to go too long, but I do want to start talking about glaciers a bit. So when I talk about glacier, okay, that's an abrupt change, going from streams to glaciers. Seems particularly pertinent. Well, I don't know if it's particularly pertinent this year or not. You look outside, it doesn't seem very glacier-esque outside, not for 1st of December, but it is that time of year. And last year we had quite a bit of snow on the ground, so we're going to make the transition. Also, I want to make the case that glaciers. Well, if we look at this picture, right, where is that picture? Oh, it's back here. If we look at this picture right here. Okay, all thumbs. Look at this picture right here. This is a good picture of an Antarctic glacier. I guess I'll leave it right there. And it's actually called, well, some call it the Doomsday Glacier. I'm not sure why. I should look into that. If you look at that, boy, yeah, that's a big piece of ice. I'm going to try to talk you into the idea that glaciers are really rivers of ice. Hence the segue between streams and glaciers. But I might be a hard sale if you look at that picture that's on the screen right there. So I better come up with some other pictures that maybe might convince you that there's some element of motion to a glacier. So the other pictures that I'm going to go to would include this one. I love that picture. Isn't that an awesome picture? This is in Greenland. This is a Piedmont/Tidewater glacier. We'll talk about that another day. But boy, you look at that thing and it looks like it's spilled out between these two mountain ranges right here. And in fact, that is what has happened. You really look at that and you can see, man, there might be something to do with movement here in glaciers. It looks like it's happened. And it has, albeit slowly, from a human time perspective. Another picture I might propose might conjure up some notion of motion is this one of a valley glacier. I think this is in Alaska. And here, boy, you look at that, it sure looks like there's even flow lines on there. You know, how can there be flow lines? Who painted that on there? You know, I mean, this idea that that thing is moving, that might not be so hard of a sale if you look at that picture right there. And that's really where I'm going, okay? A couple of examples. Now, we know that because we're warmer, about 0.7 to 1 degrees Celsius warmer now than we were 150 years ago, that glaciers are receding, and that's true. Some of you may have heard that the glaciers in Glacier National Park have stopped receding and are in fact growing. Probably not true. They have slowed down in their recession. I think we can say that. It's been kind of interesting because the park officials have had some signs out there that talked about the glaciers possibly disappearing by 2020. Those have been replaced. They're not all gone yet, but they are still receding. But glaciers have not always receded. Here's a couple of examples. Where should we go? We're going to go to the Bruggen Glacier in Chile. This is the Patagonia region of Chile. It's called Patagonia. It's believed that that was a term that was first coined or used in this area by Magellan. And it means giant or Bigfoot. Yeah, South America has its own Sasquatch legends. And I don't know if they get Jack Link's jerky down there. They mess with Sasquatch or not. But just to orient you, this is where we're looking. So we're southern Chile. And latitude is, probably not too far off where we're at here. And so look at this long, narrow fjord, how far that goes back in there, out from the sea. And this is the Bruggen Glacier here, or Pope Pio XI Glacier, named after a pope. Kind of interesting. I'm not sure if I would want that if I was a pope. So anyway, what happened in this is 1945, so this is a long while ago. But in 1945, this glacier, which was back here, began advancing rapidly. By rapidly, I mean this sucker was moving a meter a day. There was a sheep ranch in here that actually got consumed by a glacier. Now, I've looked at my homeowner's policy, and our home is protected against airplanes crashing in it. I think that's a fairly unlikely scenario, but they made a point of it in our homeowner's insurance policy. They even had a little cartoon on there. I'm thinking I'm not going to be okay, though, if a glacier smashes into my house. At any rate, this thing just moves forward rapidly over about a month's time, or month or two's time, it goes entirely across the fjord here, which this used to all be open to the sea, and it actually created this body of water back here called Grieve Lake. And you can see it's still sealed off. Another example of glaciers that have rapidly advanced, let's go to northern hemisphere. Yakutat, Alaska. This is in the 1980s, so we'll jump forward in time about 40 years. And Yakutat had something similar happen. This is a little bright here, but this, see if I can zoom in a little more, maybe dim it down just a little bit. That helps a little. This glacier goes way back to the horizon. This is the Hubbard Glacier, and this is the Marjorie Glacier that feeds into it. And these glaciers did the same thing that the Bruggen Glacier did in the 80s. It sped up rapidly. So I'm going to back out here a little bit. This is so bright I can hardly see it. It began rushing forward, and it sealed off this body of water right here. And if you think about it, that's a big deal, because this fjord is still going to have salt water or fresh water flowing into it. But this glacier right here, it sealed it off right down to the bottom. I mean, there's no salt water getting into this lake at that time. And so this water became fresher and fresher, less and less salty. And marine life in it began to die because it wasn't used to that brackish water. You can see there's an opening now here, but Marjorie and Hubbard could once again sometime flash forward again. I want to go back. Flash forward again and create the same problem. So most glaciers are in fact receding, but there are some that are not. And so but they are definitely the exception to the rule. A couple things I wanted to mention. When we talk about glaciers, they're a very unique thing. They're really like glass. Have you ever heard of glass described as a very viscous liquid, very thick liquid? People will talk about measuring cathedral glass from old European cathedrals that are hundreds of years old, and that they're always thicker towards the bottom and thinner towards the top. Some would say that's proof that glass is a very thick liquid flowing downhill through time. Others say, well, that's just because the process of making the glass, which involved putting molten glass on something, spinning it and stretching that molten glass out, created thicker edges and thinner interiors. I don't know. At any rate, I do know that glaciers are very much a very viscous liquid, if you will, because they are flowing. One of the things that I also want to mention is that glaciers never form over water. They can, I guess I want to go southern hemisphere. They can, as your notes mention, form over land and then move out over water, but they're not going to form over water, and I'm going to explain why as we talk about how glaciers form. So if we go down to Antarctica, there are a number of ice shelves here. There's a Ross's ice shelf. If I can get on. I think Ross's is on the bottom here, though. They're not going to label them. Well, yeah, right here. This is an ice shelf right here, and this has ocean water underneath it. But this is definitely ice. Well, it didn't form over the water. It formed over land and moved out over water. Okay. Now, you can have sea ice. Sea ice is different from glacial ice. Sea ice is frozen seawater. Of course, it freezes at a lower temperature, I think somewhere approaching 28 degrees instead of 32 degrees Fahrenheit, but it will eventually freeze. So you can have frozen sea ice. That's a different thing than glaciers. It is a very different thing. Glaciers are an open system, as your note said, in which frozen water, if we're using this here, frozen water would enter the system here, move through it, and exit the system here. So it is very much an open system. It's kind of like, I do cross-country skiing marathons, even after my heart attack. I'm still doing cross-country skiing marathons. Not as fast, but pretty good for a guy that's my age. And when I was first doing them, I'm from Cable, Wisconsin. That's where the Birkebeiner is. That's the largest ski race in North America. You know, I mean, my little town of 280 people, you put 60,000 people descending on it on a Birkie weekend, it makes a difference. So one year I was doing the Birkebeiner, and I was going down the trail, moving along pretty good, and all of a sudden I came to a stop. There's this line of people at the top of a hill, and I looked, and they were all being very polite, waiting for the person to go over and hopefully make it down without falling, and then the next person would go. I thought, I was young and cocky, and I thought, well, this is a race. We shouldn't be doing this. Plus, this is my home turf, you know. And so I just jumped out of line, went to the left of the people that were waiting patiently at the top of the hill. What a jerk, huh? And went down the hill and got past most of the people, and then curved back onto the trail. And as soon as I went onto the trail, one of the people that had been waiting patiently at the top, I collided with them and crashed and made a big, terrible thing. I'm embarrassed to admit I did that. And it was kind of interesting because I had created an entity by my actions. As soon as I busted out of line and went off to the side, everybody that was behind me followed me. Well, then the people that had been waiting patiently at the top of the hill saw me going by, and so they all took off. And so we all collided then in this big mass in the middle of the hill, and it was an entity that I'd created in which you had to enter one side of this thing, roll around in this mass of people, crawl out the other side, and then you could continue on down the trail. I remember being sworn at, I think it was at least 3 languages, I'm guessing, just judging. But anyway, that was an open system, just like a glacier. You had to enter it, move through it, and exit the other side. So yeah, glaciers are open system. The last thing I'm going to mention for today, because I'm already getting a little long in the tooth here, is the making of glacial ice. What does that involve? Well, oops. I thought I had a nice image here. Yeah. Okay. So we're still there's still that lingering question. Why are glaciers different from other ice like sea ice? Well, we're going to start with the formation. Snowflakes fall generally. There's a variety of different kinds of snowflakes. That snow that falls on a really cold winter day is just so light and fluffy. On average, a snowflake's about 90% air and about 10% ice. But as it ages, if you will, the corners get knocked off those beautiful snowflakes, and eventually they become more granular, and the granules become rounded like fern or corn snow. If you've ever skied downhill or snowboarded, I'm thinking particularly in Colorado, like spring skiing. You come down to those base lift lines, and boy, that snow is just like little ball bearings, and you can just become flying by there, and very slippery. And that's what this stuff that we would call this corn snow. These snows have had the edges knocked off, become more and more granular and very, very rounded. And so if you look at your notes, we're getting that porosity diminished. The pore space in there is diminished. But then as meltwater fills up those spaces, it freezes in there. And when water can no longer penetrate that ice, see if I can scroll this down just a little bit, it becomes what we call a glacial ice. Okay, it is not a glacier yet, but it is the ice that we would find in a glacier. So water can't penetrate it. That's one of the markers for glacial ice. So if you look at your notes, I talk about its porosity. I talk about it getting transformed into corn snow. Fern is that corn snow times 2. And then this is going to continue to get compressed because more and more snow is falling on top of it. Of course, if you're going to have a glacier, you got to find a place on Earth where you've got year-round snow. You can't have snow falling and then melting and then snow falling again the next year and melting to ever get a glacier. You're going to have multiple seasons. You've got to have a place where snow can stay all year and build up. And as it builds up, it accumulates on this corn snow, and it adds water to the pores and fills them up until water can no longer penetrate them because the pores are all filled with ice. They're frozen together. And then you have glacial ice. All right, I think I'm going to stop there. Didn't get quite as far as I would have liked to, but that's okay. And we'll pick it up with another lecture on Thursday.